Hello everybody, and welcome back to another Big Ideas lesson. Today we are going to be going over section 6.2, the natural base E. Before we do, I've got a scenario that relates to the last section I'd like us to take a look at. So, let's say we're opening up a compound interest account, alright? This account gives an annual interest rate of 100% with a principal of $1,000. That means without compounding it, you would gain 100% of the money you have in the bank each year. So, let's take a look and see what happens when n equals 1. So in other words, it's only compounded annually. Well, our formula for compound interest is that A equals P times 1 plus R over N to the NT power. If we plug in all of our known values, we could say that the amount of money we have in the bank is equal to the 1,000 we put in at the start times 1 plus, well, we need to have 100% as a rate or as a decimal. So we can divide it by 100. Or move the decimal place 2 places to the left. Either way, we get that that's just, it's a rate of 1. So we would get 1 over n to the nt power. Perfect. Let's see what happens with an interest rate of 1 after just 1 year. Meaning our n is 1, and we're also going to make t1. Well, we would end up with 1,000 times 1 plus 1 over 1 to the 1 times 1 power. That's an easy one. 1 plus 1 over 1 is 2. 2 to the first power is just 2. So this is really just 1,000 times 2. Which is 2,000. We would have $2,000 after 1 year. Not too shabby if you don't, or if I say so myself. Let's take a look and see what happens when we change this value of n. Trust me, this is going somewhere. This is if it compounds 1 time per year. But we talked about how with compound interest, the more you compound it, the better the deal usually is. So what would happen if n was 2? And again, we want to see how much money we would have after 1 year so we can compare these two accounts. Well, here, everything would be the same. It'd be $1,000 times 1 plus 1 over n, but this time n is 2. So it would be 1 plus 1/2 to the 2 times 1 power. Well, if I take out my handy-dandy calculator here, we can actually take a look and see what this value is. So 1,000 times 1 plus 1/2 raised to the 2 times 1 is just 2. We end up with 2,500. Would you look at that? We have a good amount of money here. Instead of it being just $2,000, we would have $2,250. Not bad at all, an extra 250 bucks. I'll take that. Hey, let's see if this pattern continues. What I'd like you to do is I would like you to try and calculate out how much money we would have if n was 4, so your interest is compounded every quarter. Then I want you to see what happens if it was compounded monthly, so n equals 12. Then I want you to see what happens when it's compounded every single day, 365. Pause the video and see if you can calculate out these numbers. How'd you do? So if we compounded this interest account 4 times a year, we'd get a total of $2,441.41. Because again, they're adding money to our account 4 times a year as opposed to all in one burst. so we're getting interest based off of that interest. At 12 times a year, it boosts up to $2,613.04. And at 365 times a year, every single day, it goes up to $2,714.57. Hang on a minute. Going from 1 to 2 added like $250. Going from 2 to 4 added like $200. Why is going from 12 to 365 only adding like 100? It actually gets even worse. Just for demonstration purposes, I actually calculated out what would happen if our interest was compounded 5 million times a year. And take a look at the difference between it being compounded every single day and compounded 5 million times a year. You're making $4 more. What's going on here? Well, it seems like we've reached some form of almost decay. It's like we're approaching a certain number. We're getting really, really close. But no matter how high we go, we're never quite going to reach that specific number. As it turns out, this number has a name. In fact, it has a spot on your calculator because it's so, so important. This number is called the natural base e. So what is it? Well, we know that there are special numbers, such as pi and I, that we have learned in the past, and their significance can be a little bit weird. Sometimes we don't know what they do all at the start. E is very similar to that. This number, once again, is called the natural base. Here's what we did in the notes here. We have a table. And this is kind of like the compound interest formula, right? I mean, shoot, if I go even to my calculator, we can see that I basically typed in something just like that. Except I had a 1,000 in front to make the numbers nicer, and the x's were replaced with whatever we wanted. Well, here x is 10, so this is like a compound interest account compounding 10 times a year. 100 times a year, 1,000, 10,000, 100,000, million. It turns out we're getting really close to a certain number. It looks like it goes 2.7182-ish. This number, e, is irrational. It's going to continue on forever. But the number itself is as follows. 2.7182818286. I am not going to have you memorize this whole number, just like how I wouldn't have you memorize a ton of pi. We will use the first 3 decimal places. 2.718 is an approximation of e. So anytime you see this e symbol, it really is just a number. Like, here, let me give you an example. In your calculator, there's actually a button for e. There's 2 of them, actually. It's so important there's 2. One of these buttons is the blue button right above the division sign. You see that e? If you type in second and then click e and press enter, what do you know? 2.718281828. Just like how if I typed in pi, like so, I would get 3.14159. It's just a number. Another place you can find e is down here, above this button that says ln, which we're going to talk about in the next section. This is e to the power of something, so it already puts a power in there for you. Let's say, for instance, I wanted to figure out what e squared is. Boom, done. You can use the buttons interchangeably. But since e is just a number, we can also treat it the same way we treat other things with exponents. It follows all of our exponent rules. So for instance, what happens when you have 2 numbers with the same base being multiplied together with different powers? Well, we learned that we can add the powers. This is the same as e to the 3 plus 6 power, which is 9. This is just e to the 9th. Done! In B, it's a reminder of what happens when you have the same base on the top and bottom of a fraction. You would subtract it. So this is the same as 16. 5 minus 4 is just 1, so it would be e to the first, or just e, over 4. And 16 over 4, that simplifies very easily down to 4. This is 4e. Question C uses a couple of tricks. So first off, we have to remember what to do when there is an exponent outside of parentheses. And that's, we give it to everything inside of the parentheses. So the 3 gets the squared, and the e to the negative 4x gets the squared. This becomes 3 squared, e to the, remember what happens when we bring it from the outside onto another power, you multiply. So negative 4 times 2 is negative 8. Are we done? No, we can keep simplifying. Like, we know that 3 squared, for instance, is 9. And what do we do when you have a negative exponent? Our negative exponent rule says we can flip it onto the bottom of a fraction. This is the same as 9 over e to the 8x. We treat e just like we treat the number 2 or 5. It's just a number. However, it has some very special properties. Let's take a look down here and see a couple of those special properties. The most interesting thing about the natural base is it creates a new type of exponential growth or exponential decay function, one which has a very, very special case. The slope of the line at any point is equal to its y value. Like this small section here is a slope of 1. This small section here is a slope of e. What this means is we can create this very natural-looking exponential growth and exponential decay curve. Natural as a natural base. The function is, as you can read from here, y equals a e to the rx power. This looks a lot like our regular exponential, y equals a b to the x. In the former, b controlled whether it was growth or decay. If b was in between 0 and 1, it was decay. And if b was bigger than 1, it was growth. But that's not the case with our natural base function, because, again, e isn't a variable, it's a number. Instead, the variable we're looking at is r. When a is greater than 0 and r is greater than 0, meaning when your r value is positive, it's growth. When your r value is negative, it's decay. This makes it so much easier to determine if something is growing or decaying, because you literally just have to look and say, do I have a negative exponent or do I have a positive exponent? It's very convenient. So if I gave you y equals 3e to the negative 2x, we don't need to ask ourselves between 0 and 1 or bigger than 1. We just say, is our r value negative or positive? Since it's negative, we would expect this to be a decay curve. Let's see it. Going to press graph. There it is. It's decay. So it's a much more convenient way of handling exponentials. It's very nice. Let's flip the page and actually talk about some applications of this. First off, yes, you can figure out if something is growth or decay based on whether that r value is positive. And if you don't have an r value, I'll always imagine a 1. So like this would be growth because this is 1x, and this would be decay because this is negative 0.5. We can also use this to graph for us. So let's take a look and see if we can plug in some of these values into these functions. I want you to focus on plugging in x values into the functions, seeing what you get for y values, then estimating those points as best you can on the graph. Pause the video and come back in a moment to check your work. How did you do? One thing I wanted to mention is, some clever students have mentioned to me, Mr. Strager, why would I want to plug in those values when I can just make a table? And that is absolutely true. You can put these functions in as equations, make a table, and see exactly what the values are. A little neat trick to save you some time. Either way, let's start plotting these now. So, to plot negative 2, 0.406, 0.406 obviously isn't on here, so we'll have to estimate. So what's 0.406 really close to as a fraction? About 1/2. So I'm going to put a dot at negative 2, about 1/2, maybe a little lower. Same for negative 1. At negative 1, it's like 1.104. I'm just going to put a dot basically at 1, just a little bit above. We get 0.3. Now, why do we get such a nice number for that, but weird decimals for the others? Remember, the a value is still your y-intercept, so it's still going to be a perfect number. And 1 is 8.155. That's like right about there. We get an exponential growth curve, as we would have expected from this positive r value, the r value just being 1. We can obviously plot the second graph as well. Negative 4, 7.3, that's about 7.5 or 7 1/3. So I'll plot it right there. Negative 2, 2.7, it's like 2 3/4. I'll put that right there. 0, 1, classic. 2.368, that's like 1/3. So this one goes like so. It's decay. Bam. It's just another type of exponential growth and decay curve. Now for the real reason we're all here. Remember the situation I talked about at the start, where I mentioned that all of these numbers were approaching something. It was approaching E. Well, obviously, bankers aren't going to want to compound your interest 5 million times a year. That's so much extra work. So they devised a formula that just uses E. And this is the continuously compounded interest formula. It's so much nicer than the clunky compound interest formula we've dealt with before that can only handle compounding at certain times in the year. This one is like something that's being compounded at all times, millions and millions and billions of times a second, and even more than that. Just remember, R is still your rate as a decimal, P is still your principal, A is still your amount, T is still your time, E is a number, so don't plug anything in for E. Let's look at this example down here below. So, there are two accounts here. You and your friend both have accounts that earn annual interest compounded continuously. Yippee! The balance A in dollars of your account after T years is modeled by this equation. So we have your account is A equals 4,500 e to the 0.04 t. In fact, if you wanted to figure out what the interest rate is, you could just multiply it by 100. That's a 4% annual interest rate. This graph shows the balance of your friends after time. And we're not given an equation here. A equals, So how can we figure out which account has the greater principal? Well, obviously, this is our principal. It's our starting amount. But what would our friend's principal amount be if we don't have an equation? Remember, the principal is how much you start with in year 0. Their principal is 4,000. So our P is 4,500. We put more into the bank for this investment than they did. We have the greater principal because we have the greater starting amount. But to figure out which account has the greater balance after 10 years, let's plug in 10 for T. So if I plug into my calculator 4,500 e to the 0.04 times 10, that will give me the exact amount of money I will have in my banking account. Let's take a look. So if I go to my calculator, I'm just going to type it in exactly as it is. No need to do anything fancy. E raised to the 0.04 times 10. Bam! We would have $6,713.21. Perfect. In fact, that's pretty fantastic. In 10 years, we made like $2,000? That's crazy. But how do we figure out how much money our friend would have after 10 years? Well, on the bottom here, it shows all the different years, right? And this is where 10 years would be. What's the approximate amount at year 10? It's whatever that amount is. I'm looking at that, and I see it's a little bit above 7,000, but not quite to 7,500. I'm going to say that the amount is around $7,300. Obviously, our friend has more money in the bank account. They have more money. But to figure out who has the better balance after 10 years, well, we could just compare the numbers. If you wanted to figure out who had the better deal, let's look at how much money we earned. So if we put in 4,500 and we got out 67.13 cents, how do we figure out how much we earned? We can subtract our starting amount to give us the answer. In this case, we ended up earning $2,213.21. Our friend went from 4,000 to 7,300 about, and they earned 3,300. Okay, your friend totally won this one. Your friend found the better banking account. Well, that's it, everybody. We're going to use this natural number e a lot more in the future. A lot. But for right now, thanks for watching, and have a fantastic rest of your day.